the Weapons Collective Edge.
Welcome to the Weapons Collective Edge. Today we're going to go over some heat treat processes that I did for some demonstrations and to get me a good reference of the steels that I have access to that will also be able to be heat treated. I'll go through the letters here. A2, D2, H13, L6, M2, M4, O1, S7, 4140, 1045, 1095, 440C stainless, 6150, 52100, and 4150. There's a lot of other steels also. There's 5160, there's 9260, there's all the 10 numbers, from 1018 all the way up to 1095. So there's a lot of variation in that. Those are just common steels. They're just a high manganese type steel. But in this case, these are the ones I had access to, and I did some heat treat processes. So I'll go through that in the video, and then I'll get back with you, and we'll end the video with a lot more of the demonstration of each thing and what it does for you. So I'll see you in a minute. Here we're going to light the forge. Turn on the propane, and spark it on. Inside, see the flame? Let that heat up. At the same time, we'll load in some steel. Steel we're going to do quenching in water. Load that first. Got a couple samples we're going to try out. Let them warm up, and we'll come back. This piece is oil quenched. See here, it's bright red hot inside there. Quench it in our bucket of oil. And I'll get that out right now and throw that in there. In there, toss it in the oil. Cools it a little slower. Some steels need it cooled slower so that it doesn't get as brittle or shatter as it gets heat treated, and that's what the oil's for. Those steels are now heated up. We're going to quench them. Quench these in water. Thin pieces, so they heat up and reduce heat pretty quickly. They're just little test strips, they're not knives or anything like that. Just quick hot piece, drop it in the cold water. I'll show you one up close on camera when I get this next one out. See there, right. Quench those, that'll harden those, and then we'll test them on the Rockwell tester. Load the part on the tester. Rotate these up. Rotate this until the dials get lined up. Just like that. Line that up. Set this over here real quick. Click it. The number reads, and we've got about 40 Rockwell. We heat the pieces back up in the toaster oven at 450 degrees. Have them sit in that for an hour, and that will reduce the hardness and make them so they're a little bit tougher, but not as hard on the RC scale. Okay, well, I'm back, and the stuff that I went through earlier was a process that a knife and sword maker can change in steel. So most steels have a chemical composition that you can't change after the product is made and manufactured. But afterwards, you can change what I did in the video there of how hard the material is. So in this case, here's a piece of wire. Wire is ductile. It has the ability to bend and not break. Where, like this hacksaw blade, this has what is more elastic, so it's straight, it bends, and it comes back, but it's also hard because it can break. And when it breaks, that's also brittle. So this hacksaw blade, which just broke, has the ability to cut this material that's ductile, or other materials that are even hard, somewhat hard. They cannot cut super hard materials, but in general, that's what that is. Same thing we've got with a piece of some bolt or some cutters. So that cuts that material, and this doesn't break. How these are made, more than likely, I'm just guessing, but this is hardened up very hard, but the back part and the rest of all the handle is softer, which makes it tougher. So you want the hardness for the ability to not be able to be destroyed in pushing on something that's softer than itself, but you get that compromise of, if you make it too hard, it'll be like this hacksaw blade and it breaks completely off. But if you get it to where maybe differential heating, I guess you'd want to call it, like some samurai swords and stuff are made, is this part's really, really hard and the rest of this is softer, still maybe hardened to like 40 Rockwell or something, where this might be more in the 50s, and even like on the hacksaw blade might even get up to the 60s. So that's what me and other knife makers and sword makers can do, is create hardness in a blade so that it makes it can cut things easier and not dull, which is a feature that all knife makers want. They want that ability to cut something and not have it dull. Here I've got a big machete. We can see it has elasticity. It can bend. Other knives of this size that were tough, this is tough and elastic, that are super hard, do this and they could probably break. An example of that is, I've got a throwing knife here that this should be softer. Like I've got down in my chart here, I'm saying that I'd like this to be 40s to low 50s, 51 maybe, and the profile was made a little too thin and the tip broke completely off. Where I've got this one that I made myself. I know what this is. This is 50 Rockwell, and I made it extra thick, so it's thick at that tip. I've thrown it hundreds of times and it doesn't break, and the tip is not too thin, so it does not snap off. Another throwing knife here. It's all cleaned up, beautiful. It is 420 J2 steel, and I have not Rockwell tested this, but my guesstimate is it's probably in 52 Rockwell maybe. And this knife, again, its profile has a pretty thick tip, and I've thrown it numerous times. It probably wouldn't break. But I've got a Gil Hibben here, and this is, it just says stainless, but I threw that, and the handle completely busted clean off. Now it had been thrown numerous times. It just probably had a bad hit, probably hit sideways. When you hit this flat against the surface, this has a better chance of breaking than if it hits where it's supposed to hit. But in this case, it might have been hardened just a little bit harder than it should have been. Again, this throwing knife is 50 Rockwell. I would prefer it to be in that range. Anything harder, and you have a tendency to break like we go here with this hacksaw blade. So overall, we're going with hardness. Hardness makes it so that I can cut and then doesn't dull. And as it gets to maybe 48, 45 Rockwell, then when I cut, it still cuts, but then it might start to dull faster. And then we go into toughness. Toughness is also where we're talking about this doesn't get bent too easily, but it also can bend and come back to shape, which is also elastic. And then we get into what we don't want really so much in knives and swords is ductility, which would be great that if swords could do this and stay sharp, but if they're this ductile where they can bend, they're not going to be sharp. And this isn't really a characteristic that we'd like to have, and it's something we're cutting with. So ductility is great, but in the case of a knife or a sword, it's not something we prefer. We'd like something more elastic, which has the ability to kind of bend. I couldn't bend this like the wire, but it comes back to shape. So those are the characteristics we're looking for. And that's what the heat treat process did. And the chart that I had gives a reference of what I could do in just a little propane forge. There's nothing special, no special heat treat processes of raising the temperature a certain way or putting it into a cryogenic thing where it's frozen or anything special. I don't know too much about metallurgy besides those numbers and being able to heat it up to the temperature where it can be quenched and it changes to martensiite, which is what makes things have that hard edge, and tempering it back so you draw that number back just a little bit so that it is more ductile but not breakable, more elastic. And the numbers I'm shooting for is what I've got on my little chart here, and those are just reference. Those are just my ideas. Other people have other ideas. Metallurgists would know a whole lot more. And if you really have a strong interest in this, I recommend you go to other websites, other YouTube videos that tell you more about metallurgy and what the core mechanics of the properties are that goes into steels, and it can totally change. That's why there's so many varieties of steels and all the ones that I read off, because one type of steel can't do everything. So if I had an M2 or an M4, it's made into a machine tool bit. Let's just say this is a machine tool bit. This is a machine tool bit, and it'll cut all these things. It will even cut this thing that's at 50 Rockwell. It can still cut this and mill into it, which is called carbide. It's super hard, but it's also super brittle. So when you take your cuts, there are certain speeds and feeds and machining that you need to know so that it can cut properly and not fall apart. So that's what different types of steels can do. Whereas if I take just a 1045 steel, which doesn't harden past, I hardened it to 54 Rockwell as hard without tempering it. And that could do a little bit of cutting, but it's not going to be like a carbide. But a carbide, I'm not going to cut a tree down with. It's going to break. And the carbide has the ability to be put onto things. Like sometimes this hacksaw blade, they'll put carbide tips on it so that it'll cut. It's really brittle, but it's in small enough quantity that it's just enough to do the property you wanted it to do. But usually don't carbide any of your knives. So we're looking at just those tool steels, what I could do with a propane forge, and that gives us a good general idea of what we can do at a home forge and not have to use heat treat furnaces and all that stuff. But overall, that's what I wanted to go over with you, and if you like this, please subscribe, and I will see you again. Thanks.